Welcome to the first Schmidt Center Colloquium of this fall. It's jointly hosted by the Eric and Wendy Schmidt Center at the Broad and EECS at MIT. In the series, we feature speakers whose work shows how machine learning is driving insights into important questions in biomedical sciences, and equivalently, how questions in biomedical sciences is spurring foundational advances in machine learning. And we're equally excited about both directions, so we're really excited to have Katherine Heller with us today. Katherine is a research scientist at Google, where she leads the Context in AI Research, or CAREER team. Her work focuses on identifying robustness and fairness issues in medical AI and creative technologies. She's made a remarkable real-world impact, Katherine. I was reading about this. It's incredible that you've developed and integrated multiple machine learning systems into hospitals and clinical care. That is hard to do. These include sepsis detection systems now running in Duke University Hospital's emergency department, a system that predicts surgical complications, and a nationally released mobile app on multiple sclerosis. Throughout this work, she is passionate about ensuring that everyone is included in the development of medical AI technology, and I'm sure we'll hear a lot about that today. Before Google, Katherine held appointments across multiple departments at Duke, and this is quite a list: statistical science, neurobiology, neurology, computer science, and electrical and computer engineering. She's been recognized with an NSF CAREER Award and was a first-round recipient of the Brain Initiative Award. Katherine received her bachelor's in computer science and applied math at SUNY Stony Brook, MS in CS from Columbia, PhD in neuroscience unit at UCL, and she did her postdoc, EPSRC, postdoc in engineering at Cambridge, and then was here across the road doing her NSF postdoc in the Brain and Cognitive Sciences department. So we are really excited to have you here, Katherine. Take it away.
Thanks so much. Yeah, I'm watching this video of like all my friends. Some of them I haven't seen since grad school, like who are coming to talk, and I'm so envious of you guys getting to see them and finding out what they're up to right now. So this is great. Thank you so much for inviting me. Okay, so I'm Katherine, and I'll be talking about some of the work that we're doing right now at Google. I know I'm here to answer people's questions on sort of like the academia industry sort of spectrum, because I've experienced both sides of that division. But I'm going to be talking about our industry-related work now. And our team is called Context in AI Research. And so I want to talk about what they've been up to, as well as doing human-centered AI research right in a healthcare context specifically, at a time when we're talking a lot about general purpose AI and how to get general purpose AI off the ground in industry. Okay. So at a very high level, this relates to, and maybe this is more of an industry thing, I don't know, but I'm going to hope, right? But like at a high level, this relates to an ICML paper that we just had on artificial general intelligence. And it was a position paper this year at ICML, and we asked in it the community to stop using AGI as the North Star of AI research. And so we talked about many of the ways in which AGI enhances known issues via what we call traps. And I'm not going to go into great detail about it, but they're all there for you to see. And so a lot of it comes down to a lack of definition of what AGI is, and how it obscures worthwhile scientific, engineering, and societal goals. And our work really advocates for specific definitions and metrics, and particularly those that are inclusive of diversity of experience and knowledge that people have. So that's what you're going to see from a lot of this talk. I'm going to focus on a healthcare context, right? So everything that I'm going to talk about is related to health, but always with specific definitions and metrics in mind. Okay, so this is our team. This is the CAREER team at Google. We're a group of people who are dedicated to developing and evaluating AI systems that are grounded in real-world contexts and use cases. with a focus on solutions that promote equitable outcomes. Having equitable outcomes is really, really important to us, and really important to the sort of the broader team that we're in at Google. Outreach and inclusion are central to our work, and everything that we do. And here I'm going to talk about the healthcare context specifically. Okay, so I'm going to start with causal modeling specifically, because it's pretty central to formalizing our questions and concerns and their solutions. We can use causal modeling to design valid evaluation procedures, which we can use with a lot of technology that's currently being developed in AI fields. And these evaluation procedures that the ones that are used currently are too often constructed in an ineffective or harmful way. Causal modeling provides a way to formally incorporate important domain-specific knowledge, which is very important in a health domain, to ensure synergy between the predictive tasks studied in the deployment context, and to more deeply understand data biases, like label or selection bias. An important part of this work is understanding how to design machine learning systems that are appropriately grounded in the context in which they're intended to be used. So this means clearly defining the intended use case and the target population. Later, we're going to see a classifier that identifies a dermatological disease in images. And so for this, for example, we'd want to define how that model is going to be used in a clinical workflow, what the clinical setting is, for which populations it's intended to be used for. Ideally, we can use this sort of reasoning to develop contextualized statements about the downstream impacts of the models that we develop. A key issue that we need to address is that the data that's used for model development and evaluation reflects complex societal context, which results in differences in health outcomes, access, and quality. So this introduces issues like selection bias, because data sets will be less representative of populations with worse access to care. And if utilization of healthcare, for example, is used as a proxy for the need for healthcare, as we've seen in a lot of different papers, this is going to result in a worse proxy for patients with poorer access to care. So we see this all the time in terms of like we're deciding on who needs this healthcare by looking at who's used it in the past, and all kinds of bias-related issues come into play. Here we're going to focus on issues that arise with basic evaluations of model performance across subgroups. So we discuss where we're interested in evaluating performance across subgroups defined by attributes like race or gender. But these can apply to any kinds of related contexts. So it can be different races, different genders, but it can also be different socioeconomic groups. It can be living in different places in the world, that kind of thing. Even in the best case where we have representative data, comparison of model performance across subgroups can be misleading because the optimal performance tends to differ across subgroups, and can be just explained by differences in data distribution across those subgroups. So I'll explain more about what this actually means in a second, but we can consider this to be a false positive fairness violation. Okay, so here we look at some of the most common classes of fairness criteria that include demographic parity and equalist odds. Demographic parity asks that model predictions be independent of group membership, and equalist odds asks that demographic parity hold conditioned on the outcome. This is equivalent to requiring that the true positive or false positive error rates not differ across groups. So again, like how well we're doing should be the same regardless of whether we're Black or white or male or female or rich or poor or from India or Pakistan, right? Like it should just all, those shouldn't be factors. Okay, so there are variations of both of these criteria that are defined for the continuous valued score S, for the prediction, the threshold predictor y hat. we can see commonly used evaluation interpretations that pop up in the research around us. So again, in people's papers, you'll see a lot of these in some various form or another. So for example, matching ROC curves, something that we see a lot of in papers, right? True positive rates, false positive rates, these can all illuminate these differences. Okay, so here's a simulated example. The top left plot introduces the notion of score distribution. So that's the distribution of scores that a model assigns to a population of subgroup. So for example, this could be like kidney functioning or EGFR. For a given threshold, the classification rate is the fraction of patients whose scores exceed the threshold, and thus would be assigned a positive prediction. So in the plot, the threshold is the dashed vertical line, and the classification rate is given by the area under the curve to the right of the threshold. The classification rate is also shown in the bottom plot. It's just plotted there, right? And then separately in the middle and right columns, we have the negative and positive class respectively, like people who do or don't have kidney disease. And so as we slide the threshold from left to right, the false positive rate in the middle column goes to 0, and the true positive rate in the right column goes to 0, in keeping with the underlying distribution, right? We're classifying fewer and fewer people as having the disease. So now, if we have two distributions, right, because we have multiple subgroups, the blue and the brown distribution, two separate subgroups, we can see how we get evaluation fairness problems. The distribution inequality creates gaps, so you can see those gaps in the bottom plots. A classification rate gap or an outcome-dependent false positive rate or true positive rate gap signify that for the same threshold, these rates are different across different groups. And so what's optimal for one group isn't necessarily optimal for another group, right? We look at the distribution of scores, we see that we have a gap, we can identify that and flag it. So to better understand and model the different kinds of shifts and differences that we see, we can use causal graphical models representing the kind of independence and conditional independence structure that we saw in the table a couple of slides back. Not only are we capable of formalizing the shifts given here, but also things like selection bias, label bias, and other kinds of confounding. And I'm going to refer you to the work of Stephen Full, who is somebody who I work with, in order, if you're interested in this line of work, to get more details and to check out some of their papers. So one specific CARER team example of bias resulting from distribution shift can be seen in a NeurIPS paper that we had a couple of years ago. Assuming that we develop a fair model, we need to understand whether fairness transfers to the deployment environment. So all the time, machine learning practitioners run into problems where it's like they've developed a model, they've trained and tested in one particular circumstance, and then they think they've captured a causal mechanism, and so they can easily transfer it to another, and then that turns out not to be the case. And this is a failure mode for machine learning. Quite commonly, we haven't actually captured the causal structure that we think we're capturing. We've captured something else about our particular environment. And so we want to be able to recognize that. So if model A is fair in hospital A, will it be fair in hospital B? Or if it works for one race, will it work for another? So what you see here is a study in dermatology predicting a whole bunch of skin conditions from images. There are two different clinical environments. One, the one that's trained on, was teledermatology in the US, and the target is clinic. It's a clinic, and it's taken from in-clinic patients in Australia. And so this involves a shift on demographics and also images and labels. And you can see the shift in demographics on the left-hand side, right? Men and women, ages of the patients, et cetera. Okay, so on the bottom right, this plot here, we can see the impact of the shift on fairness, right? With a model that was fair in training, so that would be the one with the open dots, that's the source distribution. leading to large gaps between different subgroups and deployment. So in particular, age, right? So if we look at, here, I'm going to walk over. If we look at 18 to 29-year-olds, we're doing about as well in our modeling our source distribution as we were in the in the target distribution as we were in the original source distribution. Whereas if we look at people who are 65 and older, we're doing much, much worse. And so this leads to different fairness outcomes for those two groups of people. Okay, so recently we looked at evaluating large language model question answering around answers to health questions. So this work led to evaluation done on the MedPOM2 model, which you can see. The user in MedPOM2, the user asks questions like, can incontinence be cured? And the model gives a particular answer, right? So this is like the kind of common thing that you see with a chatbot. MedPOM is Google's particular medically related, well, it was their old medically related chatbot model. And so we look at assessment on a system like MedPOM, and we have a Nature Medicine paper looking at assessing MedPOM for disparities between different demographics and bias that might insert itself within a MedPOM context. And the Nature Medicine paper that we have makes a couple of different key contributions. The first contribution is that it develops new rubrics for the assessment of equity-related biases in LLM-generated answers to medical questions. So this includes 3 modes of evaluation: independent, pairwise, and counterfactual, and I'll show you causal models for them in a second. But there are also 3 kinds of raters: clinical raters, equity experts, and regular consumers. And then after we develop these rubrics, we collect new data sets. We've collected 7 new data sets that are enriched for equity-relevant domains and which are documented and released. And lastly, we run an empirical study with MedPOM. This is the largest human evaluation study to date, or at least it was when the paper came out within the last year. It includes assessment questions and data sets which allow for identifying previously unknown limitations, and it also exhibits different modes of evaluation and rater types which allow for probing dimensions of bias. Okay, so first up, I'm going to go through those steps one by one, right? So first up is rubrics. So in order to understand fairness and equity challenges in a health context, a rubric has to be developed to understand what the definitions of these terms means. So like, what is fair, right? Like what fairness means, big open question, right? It could be a lot of different things. And so in order to tackle that, we want to ask a whole bunch of different people, like physicians. Okay, so we want to know how it's related to practical medical systems, what dimensions are relevant to measure. And so we get a bunch of physicians and we ask them. And we look at MedPOM prompting, and we try to understand what kinds of bias might crop up in the answers. And so we do this using the kinds of causal models that we've seen in the previous slides. And so we captured 6 different dimensions of bias through our procedure. And they're shown on the slide on the right-hand side. And so just briefly, the first 2 dimensions captured the idea that the outputs should be accurate and inclusive of the experiences and perspectives of all groups of people. The 3rd dimension captures stereotyping. The 4th dimension assesses whether outputs presented appropriate social and structural explanations for health disparities. The fifth dimension deals with the idea that some of the questions are explicitly adversarial and potentially contain a premise that's itself problematic in terms of presenting content that contains misinformation, offensive or stereotyping content, et cetera. And last, we aim to assess whether potentially acting on an output could lead to disproportionate withholding of opportunities or resources. And so, as I mentioned, we introduced 3 versions of assessment, of the assessment rubric that can be used for different types of design. These are independent, pairwise, and counterfactual, and I will briefly show you what these rubrics look like. So here's the rubric for independent assessments. The main thing to notice is that the dimensions of bias that we define show up as options for the raters to annotate when flagging an output as containing bias. Independent assessments ask about whether the answer contains bias, just straight up, one question, one answer. Pairwise rubric assessments look at relative bias between two alternative scenarios, right? So it's like you have a question, here's answer A, here's answer B, which one do you like better, which one do you think contains less bias? And then counterfactual assessments ask about the ideal versus the actual answers. And so what I mean by this is like actually the prompt can change. So instead of having a white person, you can have a black person inserted into the prompt, and then you can evaluate what kind of bias you think comes out of the answers to those prompts. Okay, so using the metrics that we discussed, that we collected from physicians amongst the axes of bias that we discussed, we collect the equity MedQA datasets. So that's a collection of 7 datasets of adversarial questions, and a few thousand of them are unique questions. As mentioned, the purpose of the datasets is to probe for potential bias with prompts that plausibly would lead to problematic outputs. So again, we expect more problematic outputs than you would normally find using an LLM. Each of the individual data sets was collected for different types of adversarial questions and are derived through a variety of methods, both manual and semi-automated. So for example, one of the data sets is topically enriched for content related to health inequities in the US, and another one focuses on tropical and infectious diseases. So this table gives the details of all of the data sets. For additional details, you can read our Nature Medicine paper or, again, talk to Stephen. In particular, we use the tropical and infectious diseases data set to instruction tune Gemini, and I'm going to show you a recording of that demo in a second. The final component of the study is an empirical study where we applied our assessment rubrics and data sets in practice using the outputs of MedPOM2 as a proof of concept study. An important part of this was to understand how groups of raters with different expertise and perspectives might evaluate outputs differently. So things that we do in this evaluation, again, of MedPOM2, is we apply rubrics to the equity MedQA dataset and 3 other datasets with 3 rater groups: physicians, equity experts, and consumers or patients. We do pairwise comparisons between MedPOM2 and MedPOM2 and physician written answers. We assess inter-rater reliability on a subset that mixed adversarial and non-adversarial data. We do a pilot study with counterfactual rubrics and datasets, and we analyze the demographic effects with consumer raters. And in general, I mean, I'm just gonna highlight a few of the key results and takeaways from the empirical study. Okay, so first we report a much greater rate of bias in model outputs than previous work for the data sets in common. So again, there were some data sets that were already collected in other papers. We also run this on them. and we see more data set resulting, more bias resulting from using our rubrics than those data sets were found to have in the previously studied papers. So this suggests that the rubrics work in the sense that they prime raters to identify biases that weren't seen with previous versions of the rubric that were used in these other papers. We also find a greater rate of bias reported with the adversarial data sets over non-adversarial data sets. And this indicates that the use of the data sets are actually enriched for questions where the model is more likely to produce biased outputs. We find that the use of multiple data sets, rubrics, and rater groups is useful for identifying different aspects of bias. And then lastly, we still think that this approach underestimates bias since it's a post hoc analysis. Okay, so that basically concludes what I have to say about our health equity toolbox. Again, for more information about the health equity toolbox, we have a Nature Medicine paper. You can look at it. I'm going to now focus on a particular data set in the health equity toolbox called the tropical and infectious diseases data set. And so here we'd like to understand how large language models like Gemini perform on the diseases, the tropical, more globalized diseases like malaria, and what contextual information like demographic attributes or location information impact model performance. Tropical diseases are focused on because they're less likely to be common demographically and geographically, and least likely to be captured in commonly used training data sets. So in the development of a data set that can capture underrepresented properties associated with these diseases, we focus on 4 different aspects. The first is specific properties of the disease itself, and we find that in authoritative sources. The second is the symptomology, the third is the location, and the last one is any different risk factors. These are all contextual pieces of information that we want to capture that we think will lead to like a good diagnosis in a globalized setting. And risk factors might include lifestyle, age, sex, things that are associated with the disease. And so in this way, either by manually curating or generating these details, we construct our TRINS data set. Okay, so here's an example for tuberculosis. Authoritative sources are searched and symptomology is added to a seed prompt. Then geographical prevalence is assessed and a location of focus is selected. This is if we're generating a prompt, right? And then lastly, we search for risk factors related to tuberculosis. So here we can see differing occurrences based on age and sex with increasing prevalence in men in middle age groups, right? And so that's something that we want to take into account when we generate our prompt for tuberculosis. Okay, so here's an example for sleeping sickness. We have different attributes being discussed, 28-year-old male. We have general symptoms. So they have fever, severe headaches, etc. We have specific symptoms like they developed a skin rash and show signs of confusion. We have the location of high incidence. The patient lives in the particular province they do. I'm sorry, I'm going to totally butcher the name of that province. I feel badly. And then their lifestyle factors that they discuss, like they own domestic animals. And so this in general is sort of the schema that's used for developing the prompts that we study, that we generated for the TRINS data set. And so the person enters their demographic information, they're a young woman from Dakar. They enter any risk factors that they have, right? So this could be that they slept with a mosquito net, without a mosquito net. And then they enter all of the symptoms that they're currently experiencing. So fever, fatigue, sore throat, etc. And so the next part is going to take a while, and I apologize. It actually takes a long time in real life too. It's not just this video. Yeah. Okay, so then they try to use that inputted information, and they're going to generate a summary and a diagnosis of what disease they're experiencing. And so basically, oh, here we go. So here's a summary of the case file, right? So it takes that information, it generally generates a prompt, and it says what tropical disease the patient might be experiencing. It gives some confidence measurement around that, and then you can see like an incidence graph in the world where it talks about what the incidence of the particular disease might be. And so I don't show a lot of head-to-head comparisons with Gemini. For those, again, you can look in the paper. But we will just take it for granted that this is substantially improved. Okay. We won't take it for granted. You can look in the paper. It is substantially improved. I have plots there. And you can see the improvement that it makes. Okay, so again, like these large language models have historically been quite bad at more globalized diseases, and so this is an attempt that we made in order to try to improve them. Okay, the next one that I'm going to talk about is the largest study to date on African healthcare. I think. This paper was published a month ago, so I guess since a month ago. And it collects a different kind of data called the AfriMed QA data, which I'll get into in a second. Okay, so there's an AfriMed QA consortium that people on my team put together. It includes Google Research, but it also includes a whole bunch of organizations in Africa, like Sasanki Biotech and Masakane. It involves funders from all over. And the form of this data set is going to be something like this, right, where you have like a bunch of questions like those found on medical board exams, where a situation is posed and then there's like a multiple choice response. So there's an example here, but this is like MedQA is like often like something used as a prompt for medical situations with large language models, and this is no different, but specific to the African context. So we have a 2-year-old boy presenting with a history of vomiting. So the question is, the best next step is what? And then you see multiple choice answers. And so the LLM answer and rationale is given and then rated by experts along relevant axes, such as quality or how well it reflects an African context. And you can see that rating sheet there. And that's collected together, and that makes up the AfriMed QA dataset. So both the datasets of the TRINS dataset of prompts and the AfriMed QA datasets are datasets generally that capture more globalized behavior for large language models in healthcare. And you can find out more information on them on the Google Research blog or by contacting Mercy Asidou, who's the person, again, on my team, who's really been instrumental in this work. I should say the AfriMed QA data was both used in order to benchmark MedGemma, which is Google's current medical LLM, and so you can find it in the data sheet for that model. But it also won the best social impact paper award at ACL, and was published a month ago at ACL. Okay, so now switching gears a little bit, I want to talk about about pregnancy intelligence, which is the work that we're doing relating to wearable devices and time series data for maternal health prediction. Mercy and Bonaventure Dassault, he's a student at Mila, worked on this quite a bit, and so I'm going to talk about it here. Okay, so in this part of the talk, I'm going to focus on wearable data as a digital biomarker. Time series data set, wearable data gives time series data sets, which are measured from wearable devices that you find via Pixel Watch or via Fitbit, and they present very extensive longitudinal passively collected data that can potentially enable discovery of unknown biomarkers. And so there's a growing interest in using this wearable data for health agents and foundation models because they generate proactive insights and personalized health responses provided by large language model-based agents for health. And they create time series foundational models that they allow the creation of time series foundation models that can scale up multimodal LLM use. Okay, so so wearable data can be of great use for maternal health. It's passively collected longitudinal data that can potentially enable better understanding of pregnancy and postpartum journeys, and the discovery of new biomarkers for maternal health, and give personalized pregnancy and postpartum insights. Google, or formerly Fitbit, has one of the largest data sets of wearable data collected during pregnancy and postpartum. This is on about 40,000 women. There's infrastructure that allows for rapid prototyping and experimental launching of LLM verticals. Pregnancy presents significant changes in biometrics, which can differ from pre-pregnancy baselines and recommendation systems, and agents need this knowledge to provide accurate insights. We're working towards the development of a maternal health subagent with the ability to improve accuracy of Gemini activity and sleep recommendations. Okay, so in particular, in our work, we were interested in predicting postpartum mood disorders from multiple collected time series. So the rest of this part is going to focus on mood disorders. Mood disorders are very, very common during and after pregnancy, and they're underdiagnosed and undertreated. So 1 in 8 women experience postpartum depression. There's a 3 times higher likelihood of suicidal behavior. Up to 80% experience some form of baby blues, and 85% are untreated with low screening rates. Okay, so we posit that the biometric data that we have can be used to make predictions of postpartum mood disorders and show us what good digital biomarkers might look like. We aim to leverage the large amount of maternal health data that we have to improve on studies that have pointed to this being a promising direction. So there are many, many studies that have pointed to this being a promising direction, but they've lacked potentially in numbers or a focus on particular outcomes. And here's an example of the kinds of time series that we're using to model mood disorders. So for example, heart rate and step count. As you can see, there are very obvious differences in these time series between women with and without mood disorders. You can sort of eyeball a lot of these plots, whether it's resting heart rate or step count, and sort of easily distinguish the differences in time series between the two groups. And so here you can see some of the demographics for the particular set of people who are data points in our study. So it's almost entirely white women and almost entirely between the ages of 30 and 40. And how long their pregnancies lasted, early term versus full term, as well as high rates of depression, anxiety, and sadness. Okay. So this is the data processing and machine learning pipeline that we used. So first we narrowed down to the cohort to pregnant women who we have enough data on. We wanted to make sure that like we could reliably sort of try to do prediction. A full schematic of the inclusion-exclusion criteria are given in the paper if you're interested. And so we then create features that are relative to the person's baseline rates. And this was very important. So like, what is their pre-pregnancy resting heart rate versus their pregnancy resting heart rate? And we found this to be really useful for prediction. We divide the data set into testing and training cohorts. And then because some of the classes are underrepresented, and this was really key, compared to others, we upsample the underrepresented classes through synthetic data collection. So in particular, we use a custom time GAN in order to do this. So again, upsampling, and this goes back to model training. So we use all the data, we train the model, and use the results to interpret features and subgroup analysis. Okay, so, and we were able to successfully do quite a good job of predicting mood disorders from this methodology, from this pipeline. And so you can see some of this in the bottom row of plots. The model that we ended up using was a time GAN. That's a generative adversarial network specifically for generating time series data with some modifications, most importantly, a non-stochastic latent space mapping for upsampling the less well-represented classes. For more information about the work or on this methodology, basically I'll refer you to Bonaventure, again at Mila, who's the first author. Okay, so we can also get a sense of the importance of each feature used in the prediction of mood disorders. So here we see that deep sleep is important in anxiety and sadness mood disorders, whereas light sleep and REM sleep is more important in depression. We can also see on the right-hand side that if we project the data down to 2 dimensions, mood disorder clusters separate out and are quite distinguishable, hopefully, again, to the eye. Okay, so the last thing I want to talk about is the expansion of this work to underrepresented classes, because the data that we've focused on so far here, in case, again, you didn't notice it when I showed you, is that it's almost all in well-off white women. And so we really want to be able to run this on other groups of people. So we're running a study in Ghana in partnership. Mercy is from Ghana, and so there are some great connections with the University of Ghana there. And we are using mobile devices, some of which I've been working on for quite a while, and wearables on women there, so we can eventually make these kinds of predictions with them. And we call this study the Akawaba study. We want to open source our tools for other researchers to be able to conduct similar studies and improve the representation of minority women in the work that they do. Okay, so there are several important questions to be considered as we move towards making predictions in lower and middle income countries. So how might the metrics change? What are the impacts of demographics and geolocation in general? Is this even feasible for LMICs? As well as things that we can measure that weren't necessarily available in the previous data set that we had access to. So like, is there a positive behavior change from the activities of our mobile phone? And so the passive signals collected are given here in this bubble, and they include things like sleep, activity, heart rate, variability, etc. Again, all off the wearable. And so there's also data that's coming from the set of mobile activities itself, like the surveys, as well as clinician-reported outcomes. So this would be like preeclampsia or hypertension, and then also their observation about birth timing, like was was the baby born preterm or at term. And clinician reports also include pre- and post-study analyses, which include health history as well as demographic information that might be relevant to the setting. It's actually one of the clinicians that we're working with is like really keen to get some of the health history information, which might represent things like induction, which are important to the setting. And then lastly, here are some snapshots of the app that we developed that are going to allow the remote collection of some of this data. So these are just sort of like the opening screens for the ACOABA study, intro and overview. And these are some screenshots for like the main screens, dashboards, et cetera. So we've started the study in Ghana, and we've enrolled our first 40 participants, but we have continuing enrollment, and we hope to get more patients involved and to have more results. And if you know anybody in Ghana who might be a good participant for this study, please refer them. But we hope to have more results to report back to you soon. Okay, thank you.
Thank you, Katherine. That was fantastic. I'm sure we have a bunch of questions. I could probably get you started on a few. I was very curious about the policy aspect of it in terms of actually implementing it. You know, for example, how does one establish deployment thresholds? If you have, for example, a bias of 13% recognized by your evaluation system, are there thoughts around what who would then decide if 12% is too high? Are those things that your group has been thinking about?
Yeah, no, it does. It makes a lot of sense. I think my group has been thinking more about how to accurately report this as opposed to like how to make the decisions about what to deploy. That's right, because like policy and particularly in an industry setting is like often controlled by other people, right? And so there are like execs who make that decision, and that is not necessarily really a decision. And there are policy people who are specifically employed to do that. So there's like in this setting like a real breaking up of different job roles, right? And so our job is more sort of like on the science information end and less on the like, yes, we're going to do this, or no, we're not going to do this kind of end.
Yeah, that totally makes sense.
We have our own personal thoughts, but.
Yes, of course. And in terms of the role of, in terms of the ability for you to go back to the training data, like are you able to identify the biases going back to the training data and see whether you can eliminate that at the training data stage, or is that hard fundamentally?
Yeah, I mean, that's a good question. I mean, I think to some degree we could do that, but like I mean, I guess that's a good question about like if we were to completely retrain some of these models, right? Like do this analysis, eliminate data. I think this is something that like pre-training teams are looking into quite a bit. But I think it's relatively unknown generally in generative AI land, like what exactly the removal or addition of specific data points gets you, right? Like if there's not a fixed answer to that, but I mean, I think that is an area of like further research, or can we do some kind of like influence discovery, right? Like influence functions, can we learn the right influence functions to detect like what data point might actually be making it behave in a certain manner? I think that would be really, really interesting to find out.
And the 6 dimensions that you identified, have there been any thoughts on whether you could potentially bake that into a loss function itself, such that you can eliminate bias in the model loss function, or is that not?
No, I mean, that is interesting. And we're trying to do work where we're coming up with evaluation procedures, and you're right. I mean, in order to, this is not for collecting data where you have clinicians like in mind, but if you're trying to do something automated, you're right, you need to be able to come up with a metric. And we're in the process of trying to work with people to do it, but like know that it certainly wasn't done for this work, if that makes sense.
Makes sense. Great. Well, I'll hand it over to the audience if you have questions going in.
Oh. So I work in the cancer program here, and something that I'm thinking about patient stratification in terms of patient populations is always clinical trials, right? Because there are a lot of people who might be eligible for certain kinds of clinical trials that are not necessarily taking part in them if they might want to. And there are efforts in expanding this, and I'm wondering if you have thought about ways to use these kinds of advancements in understanding where these kinds of biases come from to help do some kind of matching in that regard.
Yeah, I mean, okay, so are you like thinking like, when do I know if for example, one question that say like people at Fitbit or other places have been interested in quite a bit is like, how do I know when I need to collect more data on a particular kind of demographic? Is that the kind of thing that you're thinking of?
Sort of, but also in reverse, where like if you have someone who is eligible maybe for a number of different clinical trials, how might you want to sort where they might go?
Yeah.
Based on availability and what kind of demographics they might need and that kind of thing.
I think that there are a whole bunch of really good questions around. I hadn't even thought of that until now, but yes, you're right. You have a person actually, and it's not the other way around necessarily. I mean, to some degree, they can go out and collect more data, but you're right. Often you're presented with a person, and you need to know where to sort them. I think that there are. I mean, the short answer is going to be no, right? Like I haven't done that. Like the opposite of that is something that I've been trying to do for a long time. The way that you've cast it is again like something a little bit novel to me, but also makes sense. I think that there's a lot of room here for the improvement of clinical trials in general, right? Like in general, I mean, the best I can say is to make a plug for, in general, the people who make up like all of our clinical trials should be being determined through methodology like this. There's no reason that shouldn't be happening, right? Like you should be able to like do all kinds of like assessments where you're like, okay, I think that this particular, like there are also sort of like pairwise things where we're running into too many drugs needed to be trialed head to head with like, you know, that then we can actually pay for and staff, right? And we should be able to use things like this in order to point us to promising like clinical trials that we should be running and running those. Why that's not happening, I don't know. I think it's a funding issue. People who talk to me today are not going to be surprised to hear me say that. I think there's a real funding issue out there. But yes, absolutely, you're correct that should be happening, and it's not. I mean, in terms of like the particular demographics and bias for clinical trials that are already being run, again, I would love help at Google, like to be able to actually explore that, because I think it's super important and actually really valued in a lot of different contexts. I think it's actually one of the more important questions facing Google right now, in my opinion, because it applies not only to like medical clinical trials, but even things like, again, not sure which way it goes, but like things like, when do we know when we've like collected enough data on a particular language to be able to do like Google translation well and things like that, right? Like even outside of a clinical trial setting. But yeah, I mean, lots of open questions there, and they're great, and I highly recommend doing more research in this area.
Thanks for the really interesting talk. Is there like a fundamental difference between, say, like model fairness and model generalizability beyond just fairness being more about like sensitive attributes? So would you go about those problems differently, or are they basically like very similar? It's just as you were going through the talk, that's kind of what I was just wondering.
Yeah, so I think in a lot of our work, we treat a lot of model fairness questions as questions which can be derived by looking at sort of like the the causal structure around sensitive attributes. Is there something particular that you had in mind that can't be linked to an attribute that you think should be? No. So I think in general, we try to take a lot of these questions around fairness and sort of link them to attributes in general. Like they don't have to, again, they don't have to be attributes of a specific race or gender, but to say there are some attributes of this particular class, and we're going to look at those, and then we're going to use things like false positive and true positive rate gaps in order to identify when there's a problem. I think solutions are coming, right? But we can at least, that's a well paved path for thinking about identifying issues.
Thanks for the talk. This is really thought-provoking. How do you think about the stochasticity in model outputs as you're thinking about evaluating them?
Okay, so like so I'm trying to think of which model you're potentially referring to.
I guess it's maybe more of a holistic question, just sort of if you're saying, given X context, what does the model output? The fact that it might not give you the exact same output even with the same input. I could be mistaken on whether that's true.
No, yeah, I mean, yes, it's definitely true. So I think there's like some amount of variability inherent to all of this. That's correct. I think that if you think about things sort of like in probability distribution land, you're kind of saying you think that this is modeled well, say like by a particular probability distribution. You could represent a class with a probability distribution, and then you expect the variability to fall within sort of like the variance, say like of that specific form of probability distribution. And I think it's in that context generally that we think about different classes or different variables from which we do this.
Okay, I think we'll have to close out now, but Katherine's going to be around for a bit more. Please feel free to come over and have a chat. Katherine, thank you once again.
Thanks so much. Thank you all.
It was excellent. Questions? Thank you.
Thanks.